Welcome, geometry students, to section 5.2. We're doing a seamless transition from Charlie Brown Thanksgiving to Charlie Brown Christmas. So Merry Christmas, everyone. Hope you're enjoying the holidays. Let's go ahead and get started with section 5.2, which is about perpendicular bisectors. First thing we need to understand is some vocab. I wish I had like a cool little sound that played whenever I say like vocab, and I don't know, whatever. I have flashbacks to Bill Nye the Science Guy. We all love him. But anyway, equidistant, what does that mean? Well, aqua means equal, and then distant means like a distance. So it means equal distance. And usually it's talking about in reference to something. So if you live equidistant to your grandma's house in school, that means you're halfway in between. So equal distance. Now, perpendicular bisector theorem. What is this about? Well, if PM, as the name suggests, we're looking for this guy. So that's your hint. If PM, and that's a line, so make sure you give them the appropriate hat, which is a line hat, is a perpendicular bisector. I abbreviate perpendicular with this guy, by the way, in case you're wondering. That's what that's all about. So PM is a perpendicular bisector. Then what? What can we say? Well, let's take a look. We could draw these lines in here. Okay. So if essentially what this is saying is if these are the same distance, okay, so M is halfway, then P is going to be halfway too, and these lines also have to be the same length. So kind of like intuitive there, like you understand, you can kind of like figure that out essentially. But yeah, that's all there is to the perpendicular bisector theorem. This whole chapter, or this whole section, is kind of, I'm going to be honest, it's not very interesting. Now, it does have some applications, especially when it comes to like light, rays, radio waves, stuff like that, because, you know, those have certain properties that are perpendicular. If you look at a mirror, it comes at exactly a 90-degree angle, it bounces off. Also has some application in construction, but other than that, like, it's not particularly like creative when you do solving. Okay, so we're going to say AP is congruent to PB. I know you're probably thinking like, oh my gosh, that's sacrilegious for a math teacher to say that it's not interesting. Well, I just call it how I see it, you know? So, I'm honest. Some things are useful, some things are boring, some things are both. This is kind of both. So anyway, we have if PA is congruent to PB, so PA congruent to PB, then what do we know? Well, this is the exact opposite. So this is the converse, meaning that we're going to go backwards. So if we knew this, then we're going to go backwards for the converse so we can get the other one. So we know that if we draw in a little perpendicular, let's make it green. 'Tis the season. Okay, so if we draw on this guy, we need a, what letter? M. We'll make this guy M. Then we can say, then PM, put his little hat on, is a perpendicular bisector. So we got to add some lines because we did that. Let's make it 3 this time, just for fun. How much fun we're having. Okay, so it's essentially saying just the opposite. If we know we have an isosceles triangle, then we can draw in a perpendicular bisector. Oh, I'm forgetting something. How come you guys didn't say anything? It's a perpendicular bisector. And to me, this one's more important, more useful, because that means anytime we have an isosceles triangle, we essentially can draw down a line. We draw down a line, okay? And if it is, I don't know why it's not snapping into position. It usually does that. And if we draw a 90-degree angle there, then we know that these are also equal. So that's pretty cool. Actually, this one's pretty useful. So yeah, just put that one in your memory bank. As we go to our first ornament here, we see that we're asked to find AB. So we have to look at some details. One, we see that we have these two segments congruent. That makes this point a midpoint. And we see that it's perpendicular. So what do we have here? We know that this line here, B, and we can call this M, I guess, is a perpendicular bisector. Okay, if that's a perpendicular bisector, then we know that AB is congruent to BC. So this is some good old-fashioned equation practice. We get to say that 4x equals 6x minus 10. I always like moving over the smaller of the variables. Combine the variables first when you have variables on both sides. So we have minus 4x minus 4x. We get 0 equals 2x minus 10. We're going to add 10 to both sides. And we're going to get 10 equals 2x. And we divide by 2 to isolate the variable. We get x equals 5. Now, don't just circle 5 and say that's your answer. Why? Because it's asking for AB, not for x. So what does that mean? We're going to take x equals 5, and we're going to plug it in for x. Okay? And we're going to get 4 times 5. Guess what that equals? 20. 20 units. Okay? Now, you could also plug it into this x. Do you get the same thing? You should if you did this correctly. So 6 times 5 minus 10. 30 minus 10, my goodness, we get the same thing. So 20 units is AB. And we're done. That's all there is to it for the first ornament. Okay, we're going to get to another kind of odd, very specific property, which is the angle bisector theorem. This one's more important for like rays. The other one we were talking about was more important for triangles. This one's more important for like, when I say rays, I mean like rays of light. If you're designing like a headlight or something like that. But anyway, there's some engineering properties for this, is what I'm trying to say. I'm trying to make this relevant, people, okay? This math is interesting to you, or find it interesting. So QS bisects PQR, okay? The reason why we know that is this guy right here, these two. SP is perpendicular, blah, blah, blah. This one's perpendicular, blah, blah, blah. Okay? So, yeah. Let's go from there. What can we say if we know all this is true? Well, this one's kind of odd in my opinion. We know that these two lines are going to be equal. So PS is going to be congruent to RS. And that's it. All this for that payoff. You're probably like, wow, that was kind of a waste of time. And I'm like, yeah, that's what I was saying. That's what I was trying to say. This kind of just an odd property. So then we have the exact opposite. If we know these are perpendicular and congruent, okay, blah, blah, blah. And I'm so sorry. This one's not very fun for me. Like I said, this section is just kind of oddly specific. But, you know, it does have its uses. So, yeah. So then we say that ray QS, give him the correct hat. There's his hat. Starts at the Q, goes through the S. S. And QS is an angle bisector. So we're going to give them some congruent angles here. Let's make it 2, just for kicks and giggles. And there we go. We have QS as an angle bisector. Angle bisector. Let's underline that in purple for effect. Okay, so we're at the second ornament. Don't you like these ornaments? Designed them myself, by the way. Okay, so we have RM. We're trying to find that. Okay, we got a lot going on here. Guess what? We got an angle bisector. Okay, that's pretty cool. We have perpendicular lines. Okay, that's pretty cool. So we basically are going to use this first property here, the angle bisector theorem. So we know that those two segments are congruent. So we're going to say 7x, which is RM, is equal to PM, which is 2x plus 5. Again, if you have x on both sides, you're going to subtract the smaller x to combine like terms with the variables first. Divide by 5, divide by 5, you get x equals 1. Again, make sure you plug this in. We're going to plug x equals 1 into there for RM, and we get 7 times 1, 7 units. Okay, and that's all there is to it. It's like super specific problems. They're not much more complicated than this. There's a few wrinkles that makes it a little bit more difficult, but that's pretty much it. I don't have a lot, me personally as a math teacher, I do not have a lot of these questions on my test just because it's just like, it's an excuse to do equation practice. So this is not an emphasis for me. Ornament 3. What is the relationship between AC and BD? Duh, it's perpendicular. AC, DB, perpendicular. Okay. Oh, between AC and BD. So AC, here, we'll just be more specific. AC is a perpendicular bisector, how about that, of BD there. That's more specific. So don't just put perpendicular like I just did, and I said duh, like it was obvious. I'm sorry. I take that back. What is the length of AB? Okay, AB. So we want to know, where is it? AB is this length right here. Oh, okay, so actually this is a little bit tougher. Cool, so we have here that, no, that's not AB. Oh my goodness. That's A. I was like, oh, we don't have enough information. All right, AB is this guy, and we know what's congruent to this guy because of our first theorem up here. What is it called? Perpendicular bisector theorem. Okay, so we know it's perpendicular or it's congruent because of that property. So we're going to just say that AB is 15 units. Don't forget the units. What is the length of DC? So because this is the same line here, it's like the same thing on the other side. It's still perpendicular. Okay, just be like, oh, it's only perpendicular on that side. No, it's perpendicular on both sides. So this is still perpendicular. So that means that these are also congruent. So we have DB, or DC is going to be equal to BC. So we're going to say that this is 18 units. And that's all there is to it. If there was an equation, you could solve for the equation. You know the drill. Like, it's not super complicated. But that's it. That is section 5.2. I hope you enjoyed it, or at least I made it a little bit more enjoyable. And I hope to see you next time on West Explains Best. Take care.